So, lecture 9.1 on metaprogramming. Metaprogramming is a bit of a funny word. It's a loaded topic. We've called this lecture a bunch of different things in the past. Sometimes we've called it advanced templates. Often the idea of metaprogramming is the idea of writing a program that writes a program. That's basically what metaprogramming is. So if you could write code that kind of outputs other code, sometimes you might have words in your head for that, like transpilation or something else. And, without kind of oversimplifying it, because it is hard just because like transpilation is kind of a way of writing programs that write programs. But it's more saying that there are things we can do in C++ that when we write it will actually output something final. And you kind of know a little bit about metaprogramming through probably hash defines or something, the idea that you write something and then it kind of produces a different output. But we're going to dig into it in some really specific ways. So don't get caught up on the word. It's not really my favorite word to encapsulate a lot of this, but it does still involve a little bit of it. So first thing, lots of fun. There's something called decltype in C++. C++ essentially has a type of function or a type function. You're probably familiar with this in languages like Python or JavaScript, where you can there's a function that exists where you can pass in a value to that function and it returns a type. If I jump ahead to a code example here, it's kind of like this. So if we kind of first start on the examples, if I have a piece of code where I say int I, so I'm basically creating a variable called I that is an integer, and then I create a reference to I, so I have an integer reference now to j. That reference might be in the wrong spot. My bad. Now what I can do is if I want to create another variable called x, right, that is an int, I could write int x, or alternatively, right, if I just say copy this code here and I go and dump it here, I could either come along and say int x, or alternatively, I could say decltype I x. And in this case here, I is a value, and we're converting that value to a type. So I as a type gets converted to the value int because the type of I is an int. And I could also do something here as well where I say, you know what, I'd like to create another variable called y, and I want it to be decltype of j. So what's the type of j? It's an int reference. Okay, what are we going to do there? Can this work with auto syntax? I don't really know how it would, because auto is just auto in a lot of ways is just a similar thing to decltype. They're kind of like a way to just ask the compiler to write the right type in for you. And you'll also see here if you do something like decltype 5z, that kind of works. Now, do we need the double parentheses? That's a great question. We'll come to that. So firstly, there are rules that govern what decltype is. The full set of rules, no, it's just a bad link. I'll clean up that link after the lecture. This is the full set of rules, decltype specifier. They outline it in great detail about how it kind of works. But in general, it's like if expression E is basically a variable in the local scope or a variable in the namespace scope or a static member variable or a function parameter, then the result is variable parameters type T. Basically, in this case, it's saying if expression E is just a standard variable as you would expect it, then you're going to get that type underlying it. It's a little bit redundant in what it's saying. It's saying if the expression instead is an L value, i.e. it has a reference, then the result is T reference. And then things get a little bit weirder. You can see in this case we're saying that if E is an X value, then the result is an R value reference. And if E is a PR value, the result is just T. This stuff is well beyond the scope of the course. It used to be included in a really old version of the course, but we kind of stripped it out, a few of us who were running it, because we just felt it was kind of way beyond the scope of things that matter. Because previously we've kind of talked about R values and L values, and L value is something with an address, R values not. But the R values actually go deeper. If you, goodness, sorry, I do have to fix up some of those links there. The R values go deeper because it goes like this: R values, L values, X values, GL values, PR values. This was just an article we found some time ago that we found was really useful. The good thing about C++ is that it generally, doesn't change a great deal. So some of the older content's really good. You can see here, for instance, PR values and X values are both types of R values, as far as I remember. But an X value is an expiring value. It refers to an object usually near the end of its lifetime. And this is my favorite definition, though. A PR value is an R value that's not an X value. Now, I couldn't tell you right now to give you some good examples about, the differences between the two. But what I can kind of tell you, just to help you out, is like, if we have a function here, where, like, what's an example? Void blah. When they talk about things like an expiring value, if I create a variable called I there and I return I, obviously, sorry, that's a L value, like this, then, what they get into is like, when we talk about expiring things, obviously 5 is an R value, but it's not going to exist for very long in theory. I don't want to use that particular example because it gets into the literal sense. But the point of all that is don't worry about all of that because it's really complicated. In fact, we didn't even ask you to understand the rules of that. The point is that you can read up on them if you would like to. In particular, we don't actually really do much at all with testing you on the details of decltype. We've kind of taught you enough. A lot of this lecture is going to be a bunch of stuff that we're just kind of like, hey, it's good to know this a little bit. But you don't have to know it perfectly because there's already a lot to know. But we'll still kind of click through a few of them. I'll come back to the questions about the double parentheses. I think that's something to do with L value. I'll try and get that off the top of my head. I'm not sure though. I might have to rain check you on the double parentheses, but it definitely has a relevance to do with the fact that it's a reference. So yeah, I might come back so I can make sure that's exactly right. It's all well and good to talk about decltype and the rules, but I don't think it's really fun to have language features that just have rules and then be told that they're important. I think it's more important to understand how exactly do we use these things. So one example of how you might use a decltype is if you're writing, say, a find function. Let's imagine you're writing the STL algorithm function. You've got a templated function here. It takes in an iterator to the begin of an STL container, an iterator to the end, and an index. So it wants you to kind of, well, not a find function, like a, what is it called? Like a next function, or one of the ones that iterates through at a certain amount. So what we do is, we say for order it equals begin, int I equals 0, loop while begin is not equal to end, increment the iterator, increment I. If you manage to get to the right index, as in count that many spots, return this here. Otherwise return end. But the interesting thing is, what's the return type of the function? We know that the return type should be decltype of star begin, since we know the type of what returned is star begin, right? So what we mean by that is that, like, begin in this case, or iterator, because iterator is just left to begin, we know that's the type, but how do we specify that specifically when we don't exactly know who's going to use it, right? Because iterators are these nice generic types, but what is it iterating over? We don't exactly know. Shouldn't the last semicolon be a comma? Yeah, you're right. Yeah, here, that one should be a comma. So what we do is, this is using the new function syntax, but obviously we could go and write this the other way if we wanted to, right? So like if you think about this particular piece of code, you could write it like this, or alternatively, you could do the old C style thing and say, yeah, decltype begin. And this is really, really useful because what this basically means is, like, you're kind of deferring the concreteness of the type to the compile time, which makes this even more generic, really, because you are actually returning a value. So if you were writing a function, for instance, that didn't actually need to, how would you put it? Like, it didn't need to actually return a particular, like, unknown type, you wouldn't need decltype. But in this case, because it returns an actual element of that container, you need to specify that it's going to give you an element of that container. So go return it. Again, let me rain check you on the double brackets. There's a detail there that's escaping me at the moment. The next few things we're going to talk about are all going to be type transformations, type traits, and bindings. This stuff's, I think, pretty interesting. A little bit more maybe practically useful and potentially relevant for some assessments. First one is type transformations. We talked about type traits a little bit last week, but type transformations are basically forms of metaprogramming, I guess you'd call them that, where we're able to transform types on the fly. This is a good example. Yeah, a little hint there, I guess. This is a good example where we have this function here called print is same. And what we are doing is we are calling std is same it's kind of let's look it up. So if I look up std is same, this is something that's baked into C++. It was introduced in C++11. And basically what happens is if T and U, which are the two templater types, are the same, then the one single, then basically instantiating this function, I believe, returns true. Because you can see here what we're basically doing is printing the value of the construction of it, or in this case here, I think it's just calling the operator function there, essentially. So we're calling that particular operator. This is the thing as well. I think what's important is like sometimes you'll see with different C++ versions that they do different things. Like sometimes you see older ones will do something like this. This was just a way of using static properties to carry information. This particular one looks like it's using an operator from what I can tell in this case, which is really interesting. But the point is that something like this will be able to be compiled essentially to true or false. That's what it does. And what this means we can do when we write a program is if we write a program and this bool alpha thing just changes the printouts on the terminal, and we can run that, is if you try and print int, it's true. If you print in reference, it's false. Int r value reference, it's false. Int remove reference of int type, int remove, like these are the type transformations here in particular. I would say like what you're actually looking at here is probably type traits, because you've got type traits and type transformations, and type traits are really about analyzing types and their traits, whereas type transformations are about taking a type and turning it into something else. If we have a look at our code here and I go into the build folder and I make transform 1, I just need to make this terminal slightly smaller. Oh, will this not work? Yeah, sorry. I will come back to decltype. There was a bit of a conversation earlier about like whether we should even talk about it much, so I'd probably glossed over it quickly because I was like very much debating whether, because we've kind of ummed about decltype for a few terms, but this, I will come back to that at the end. This stuff is still relatively important here with the type transformations. 9.1 transform 1. Oops, sorry, is that the right, is it 9.1? Yeah. Oh, it's in build. Got to stay in build. Yeah, so if we kind of analyze this for a second, what we have is, yes, okay, obviously ints and ints are true, those two are false, and then the rest are all true. This here is a type transformation. It takes in an int reference, an L value reference, and it simply returns an integer. This one takes in an int R value reference, it simply returns an integer. This one takes in a const int R value reference, and you can see that it returns a const integer, which matches this const integer. Now, if we tweaked these things, of course, we would get different outputs, right? So, for instance, if I was to say remove the const part here, and we compared an int to a remove reference of a const, an R value const reference, you would see that it now should give us false at the end, right? So, because you have different ones here, you have some that remove R value references, you have some that remove L value references, or just any kind of reference, or const, or something else like that. You'll also notice that this particular one, it communicates this information this way too, with that type thing I mentioned, because when I look up standard remove reference, the way you access it is going to be, where is it, member types. Yeah, the type referred to by T or T if it is not a reference. Basically that's a particular type in this case. That's not a value. So type there references a type. and it's hard because you have to really sit down and think about some of these things, because print is same. That is returning a value. Like the result of that is evaluated to a value. The result of this is evaluated to a type. And that's quite true for a lot of common type traits. A lot of type traits are going to return you a type. A lot of type traits are going to return you a value, and a lot of type transformations are going to return you a type, which just makes sense if you think about it intuitively as well. So yeah, that's just one example of type transformations. Another example of type transformations is the ability to add references. In this particular case, we have the addition of an R value reference. So if I add an R value reference to an int, or an int reference, or already an R value reference, or an int pointer, what's going to happen there? Are they all going to be R value references? So what I'm doing on lines 12 to 15 is I'm comparing, hey, is A, B, C, D, tell me if they are the same as an R value, an R value reference to int, a non-const R value reference to int. So what we'll see there is, if I go make transform 2, it's already made it, I guess. 9.1 transform 2. Have I? Let me just double check. Oh, okay. Strange. Was there a problem in it? I gotta redo it, I think. I don't know why I commented that out. That's odd. Yeah, so this I think is really telling and interesting, personally. If we have a look at this for a second. Yep, transform 2. So we get true, false, true, false. Now that's really interesting. If we add an R value reference to an int, it turns into an int R value reference. That's somewhat intuitive, Kind of makes sense. If we then take a L value reference to an int and add an R value reference, it says it's not the same as an R value reference. If we take an R value reference and turn it in, add an R value reference to it, it's also an R value reference. And if we do a pointer, it's not the same either, which kind of makes sense. The pointer one probably makes the most sense, because it's like, well, now you just have an R value reference to an integer pointer. But this one's kind of funny, and also how does if you like R value reference and R value reference, how does that work? These are interesting questions that are answered through, where is it? Let me just find it. Do we cover it? We do cover it. I know we cover it. Yeah. So maybe we remove the rules to avoid the confusion, but basically what happens here is there's a concept going on. If you kind of, a lot of you are clicking in pretty quickly to I said this is a mishmash lecture of things that aren't as strong. There's this idea called reference collapsing, and since C++ 11, or I guess, reference collapsing are basically the rules that affect what happens when you kind of like keep referencing stuff. Like when you go and create an L value reference of an L value reference, etc. And this is a pretty good table, I guess, to have a quick glance at. Again, this is way beyond the scope of the course, what I'm talking about here. It's more just for your general background. It's like what we're showing here is essentially like if you have a int and you add an L value reference to it, it turns into an L value reference. If you have an int and you add an R value reference to it, it turns into an R value reference. That makes sense. That's basically line 5. If you have an L value reference and you basically add an L value reference to it, it stays as an L value reference. But this line is kind of where things get interesting, because it reflects line 6 here on the right, which is saying if you try and add an R value reference to an L value reference, you get left with an L value reference. And similarly, if you add an R value reference to an R value reference, you just end up with an R value reference. So these are rules of the language that help you understand how things pan out when you essentially add these different types of L value or R value references to stuff. And this little piece of code just helps you kind of see it quickly, really. Very confusing stuff. Again, very fringy, as I might call it. Since C++ 14 and 17, this is kind of what I was referring to earlier, they have managed to get shortened type trait names, which is pretty cool. So instead of having to do that stuff where you do like, add R value reference, : type, or this for values, type traits values, type transformation types, you can actually now just say, yep, standard add R value reference, and that itself is a type. So this is some nice type syntax where you can basically say, I'd like to create my new type called A. It's basically a type def, which is equal to int with an R value reference added to it. And same with the is same thing. You don't need to kind of go and invoke like : value or call the operator. You can just use them as is. That was obviously a language feature introduced because they would be commonly used. So it's nice to kind of use it a bit more conveniently as well. This topic, I think, is actually one of the more useful ones. You could talk about this for hours. I'm sure some really smart people could talk about it for a long time. But in essence, at the simple level, this is a table that helps you understand what types of arguments I can pass into what parametered functions. This is something we did talk about a little bit some weeks ago, though I think it's probably going to make a little bit more sense now, I guess. If you have a function, what was the example we talked about? It was like, if you have a function that accepts, say, blah, and it accepts, an int reference a, like this, and all that does is increments it by 1. Call it increment. If you then have a main function, and what you do is you create a variable called num, which is 0, and then I call increment on num. This works, and this works because int here can be given to, like, int can be treated as an L value reference. But what doesn't work is if I try and increment 4. And we've talked about this because the increment function, the parameter of the increment function is an L value reference, but what it is expecting to have passed in is an R value. And what this table we're looking at here is basically showing you what can you pass in different scenarios. So for instance, here it's saying that if you have a function that has an L value reference parameter, which is what I have up here on line 1, it can only take in L values. It can't take in an R value, it can't take in a const R value, and it can't take in a const L value. This makes a lot of sense actually if you think about it, because just at a basic level, for instance, you can't pass an R value into something that might modify the reference, because this function modifies it, and you can't modify the int literal for. You also know that if you try and create a const int num2, you can't pass in num2 because it's const. This one's an R value. You know that. And you know that you also can't pass in a const R value, which is a bit of a funny concept. I guess a const R value would be like if you have a function that returns a const int, like returns 5. But I've always found const R values weird me out a little bit because like R values are generally treated quite often as const, if that makes sense. So you can kind of disregard it a little bit for understanding's sake. But then it's like, well, what happens if the function now takes in a const int reference? Well, now it gets really interesting because a const int reference can take in obviously both a const L value and an L value. Makes sense. But because you have agreed to not modify it because of the fact that it's const, the language rules allow you to pass in R values and const R values, because even though like you're taking something that's meant to have an address, right? Because that's how we think about L values. Because you're not going to modify it, if you're not modifying something, you don't need to know where it is in memory. You just need to know the value of it. That now suddenly works. And similarly, if you have a function that takes in an R value reference, like a move function, you can only pass... Oh my God, I made a mess. You can only pass in certain things as well. So functions that take in R value references can only take in R values. One of the weirdest things though, it's very weird, is that if you have a function like this, you know, a const L value reference, you say, is a great parameter type because everything binds to it, is what we're saying. You can pass in L values, const L values, R values, const R values. But if you're dealing with templates, it's a little bit weird, I think. But if you have something like that, and then you have your increment function, and you're passing in a type T, the thing you always want to pass in is actually a R value reference. When it comes to templates, an R value reference binds to everything as well. We're not really going to spend a great deal of time talking about why that is. It's more something that we wanted to kind of give some background to and be like, hey, this is really important because once you start dealing with templated types, if you want to bind to everything, you need to be doing that essentially. And we can kind of see this with a couple of code examples. Let's pull some of these up. So here, yes, the first one's not templated. This will probably demonstrate it a little bit more for you. It's kind of like what I wrote. I've got a print function, takes in a const string reference. Great, okay, everything should bind to it because it's not trying to modify anything. And then I've got another function called goo, which here returns a string constant, or an R value in this case, which is that. So let's have a look at some of the examples. Firstly, I'm going to go create a string here, C++. That will be an L value. Sorry, Tim's just asked a question. I don't really get the language. Something binds to everything can be binded to by everything. I think it's fair to say that const T reference can be binded to by everything, and template R value reference can be binded to by everything. That's probably like just a little slight tweak in the language that would be causing that potential trip up. So that's a good question. So here I have a L value. It's a mutable L value because it's not const. And here I have an L value reference because I am saying, actually, sorry, is it an L value reference? Const, yeah, const L value. Yeah, I guess that's going to auto itself. Yeah, sure. So you'll see here, in the first case, when I just passed in C++ into the print function, it's passed in as an R value, which works because it binds to print. Sure. When I pass in goo, goo is also an R value because it doesn't kind of have an address in memory. It's basically been returned. When I pass in J, which is an L value, a mutable L value, it also works. And K here is a reference to this particular item here. I have to say though, having looked at this, I'm trying to digest exactly what's going on here because this is obviously a string literal, and I'm trying to figure out what type K is. Because normally if you just make something a string literal, it's a const char star. And I'm kind of intrigued by the idea of, but this is the thing, it's like a const reference kind of works. So if I bring up the code here and I say make bind 1, right, makes sense, it works. Oops, 9.1 bind 1. That works. What's interesting, of course, about C++ is I think if I just say auto reference that, it shouldn't work. Unless I've got my head mixed on wrong. Yeah, so this is where I'm actually like a little confused, is that a reference to that, because then in theory I can change it. How would I change that? Does that work? Cannot assign to variable K without const qualifier type. Or with const qualifier type. Huh, I wonder if it just adds that constant for you. There's a semicolon problem there. Yeah, declared const there. Yeah, I was going to ask, because like, obviously like the idea of a const reference. See how these two errors here are like identical basically? Makes sense, right? Because if you have a reference to, like you can have a const reference to a string literal because like, it's not the, because we often use references to modify stuff or just to save on performance when we're passing it through. But since a const reference can't be modified, it doesn't really matter that it's a string literal. Anyway, point of all of that, me playing around, was that k is, even with or without the const, k basically behaves here as a const L value. It's an L value because it is a reference and it has a memory address. It's something that you can kind of, point to. But it's const because it's referring to a string literal. Obviously, the other equivalent of this would actually just be to create a const reference, auto const reference to j there. That is how you'd do it. But obviously, without the const, that would just create a non-const reference to j2 in that case. So, yeah, that was a fun little adventure. But the point of that is that that's the non-templated example. The templated example looks like this. So if you were making a templated function, you would try and make it like this. I think there's obviously the questions that are like, wait, so const t ampersand doesn't work in template. Let's try it out. Actually, let's do it with the templated version first. So in theory, this is basically the same code now. It is literally the same code, except this doesn't say C++, it says test. So if we try and run this one now, 0.1 bind 2, we see print 1, print goo, which is the string, print that. So that still works. Let's play around and see what it does like this. Cool. So it's not so much to say that, when you go to templates, you can't do stuff. It's more saying that in templates, like a templated T, like that works with templates. Whereas if I go back to bind 1 and I just simply said, everything is a string R value reference like this, then that won't work now because it's like you're trying to assign L values to R values. Now, naturally, the reason for this, at least my best explanation of it, is like when you're not dealing with templates, it's very literally this type. Whereas like when you are dealing with templates, part of why we showed you some of the transform examples earlier is because, if you think about it, if you have like a T ampersand ampersand, and then what happens is you pass in a type that's like int reference, what happens is it tries to like kind of absorb, like if T is int reference, and then you're like, I want the R value reference of this item here, it's got to kind of do all that reference collapsing stuff, which again is way beyond what we're talking about. But it's to do with the fact that templates are like undetermined yet exactly what they are. You could pass in an R value reference that it tries to get an R value reference of the R value reference. It does all that reference collapsing stuff. And you just end up in a scenario where it can effectively bind everything, which is cool. Because remember, T is just a placeholder. Because I've seen in the past when students will talk about this stuff, they'll be like, yeah, but T is not const. It's like, well, T can be const to some extent. It's because of the type parameter stuff, because T could be anything. T could be like a constant reference, things like that. But again, I'm not gonna pretend that I'm all like hunky dory about this stuff. This stuff is very confusing. It's really at the deep end of all that compilery stuff that I've mentioned throughout the course that exists, where it's very academic. It's very like, this is a conversation that does not happen every day with a C++ developer, but it'll happen a lot more with someone who's writing compilers for C++, for instance. So that's kind of the crux of binding. That's actually, it's a useful thing to know, just the idea that like a R value reference to a template or type can bind to everything. So I do think these two kind of slides are pretty critical in your understanding. And obviously the type transformations there. Const expression. This is one of the other tidbits we're going to chat about today. Const expression is a really cool thing. Basically, yeah. I'm just double checking that something makes sense for you all. Basically, const expression is where if the compiler can calculate something at compile time, it will calculate it at compile time. I'll give you a good example of that. So this is a factorial function, and I'm going to go and copy this into Godbolt for us. There we go. That's what I wanted. So let me just play around with this code a tiny bit for you. Get rid of that. Get rid of this. 9 factorial max n. It should compile now. What's the problem? Oh. Ten factorial. Oh, okay, 9 factorial. So I've got a function here that is basically calculating 9 factorial. And this is an idea. This isn't unique to C++ necessarily, but what I want you to think about for a second, this helps you understand metaprogramming. This on the left is a set of instructions that you've written as a programmer that tells the compiler how to output a set of instructions written in machine code that someone can run those set of instructions whenever they want to calculate something, right? So what actually gets outputted here is a main function. It takes in, then someone calls another function called factorial. They pass in 9, they move it to a register, all that kind of stuff. And then the 9 factorial function will go do all its, push, pop, stack stuff. And it will, have an if statement. That's what the jump is for. And then it'll call itself potentially, right? It's a factorial function. It calls factorial 9 times factorial 8 times factorial 7. You know what I mean? Like it does that. Now you get that. And it makes sense that code compiles to it. However, what's interesting is there's some problems like this where sometimes we need a value like 9 factorial. However, there's nothing actually there's nothing external that it's dependent on. Because if you think about a lot of programs and functions, a lot of them are dependent on external input-output. They're dependent on things like what's the user typed in on the terminal? What have we read from the database? What are we pulling from the network? But in this case, 9 factorial is knowable right now. I could calculate it, right? Like I could just go to Google and type in 9 factorial. It's like 360,000. So why does it make sense to have a program that outputs the instructions for something that's totally deterministic? That's basically the point. So the rules of const expression, the rules of const expression basically say, hey, if you go and put const expression on a bunch of your things that can be calculated in real time, we will do that for you if we can. The tricky part of it is that you often need to put them in the right spot. So for instance, if I just put it there, you'll notice that, what's the error? Or maybe I'll just let me do this one in the terminal. Const expression. Yeah, let's get this running first. Be easier with I want to show you the errors that we get. So in this case, if I go and make const expression like this, right? 9.1 const expression. Yep, I get that value. Sure. If I put const expression here, here we go. It says constant variable 9 factorial, this one here, must be initialized by a constant expression. Function factorial cannot be used in a constant expression. Basically, it's saying you are trying to compile time calculate this variable 9 factorial, but you're saying the value is something that I cannot compile time calculate, and that's because I need to mark the function as const expression. And when I do that, it will suddenly compile, and voila, we get an answer. But if I go back to our compiler here, by adding those two const expressions, have a look, and this is so interesting, have a look at the program output now. What we have done is we have created a C++ program that is simply, the machine code for it is to simply print out 360,000. So when you run it, there are no calculations. What this does is it finitely slows down compile time, right? Because think about this for a second. If I don't have the constant expressions and I create a massive factorial like 50, I have no idea how big that is. It's probably quite large, right? Notice it compiles quickly for same time. I wonder if I can time that. Yeah, 0.12 seconds or 40.1.3 seconds. 0.1 again, 400. 0.4, you know what I mean? As I have a bigger number there, it doesn't take longer. However, what's interesting is once I mark it as const expression, the compiler is now going to try and do those calculations. So you'll notice that it's going to be pretty quick for the low numbers, but I imagine it's going to get really slow. What happened here? Oh, what have I done wrong? 10? I was going to say, I thought it ran out of memory. It probably did. No, it's still pretty quick. I've never actually timed it before. Number's too big. Yeah. I was hoping... I haven't normally run the timer on it. I was kind of hoping it would be obvious that it's taking so long. But it looks like it's just not having it at all. There's probably rules around it. There you go. That's what we get for experimenting. About 11. I wonder when it gets too big. 12. Yeah, I'm not happy with that. There you go. So, I mean, maybe that experiment wasn't very exciting then, but you can still imagine it. That was just meant to be demonstrative of the fact that, like, because you are pushing things to compile time will take longer, you know? Because you're not printing out the recipe to make the cake, you're actually making the cake. That is often a good thing. Oh yeah, change it to a long. Is that the problem? I don't know. Let's try it out. Now we're experimenting. Oh, I don't know. Long. Oh, there you go. Didn't realize it was the type size. Still compiling pretty quick though. 50 is probably going to be way too big. I'm so interested that it can do that so fast still. 'Cause that's a large number, I imagine. What this looks like here. Yeah, just very big number. It's interesting, like, I tried to show you how the more complicated the math it has to do, the longer it will take to compile. But in hindsight, even for myself, like, what I've clearly learned from that experience there with you all is, like, even for very large numbers, the time to calculate for something like a factorial is always going to be significantly less time than before we run out of memory. Not memory like the size bounds of a type, you know, which is really interesting. It'd probably be more interesting for like a function that, you know, added 1 or something a million times. Yeah, Suluk says, I just read this actually, you can't have a constant expression if its evaluation leads to out of bounds. Yeah, so clearly that's the compile error that we were running into here. It's interesting how, oh yeah, it's outside of the range of representable values. Did I miss all that each time? I did. Silly, sorry. Should have read a second line. Well, it was fun. That was fun to kind of explore that around. But basically, point is with constant expression, values can be determined at compile time means less processing needed at runtime. That's great. It shifts the potential source of errors to compile time as well, which is true. That's an interesting thing, isn't it? Because if you have a for loop that is just adding, you know, multiplying numbers together at runtime 50, you know, if you think about it, it's really interesting. Because if I got rid of this constant expression, right, what would happen now if I did factorial of, say, you know, 50, that, or 22 even, that doesn't fit inside a long, but the compiler, get rid of this silly time thing now, the compiler will actually still make it work, right? But when I run it, what's going to happen? I get this. This is clearly going to be some kind of overflow situation, which isn't good. So the point is, I think that's what I'd really like to highlight with that second point. By shifting these calculatable expressions to compile time, we in effect, they call it shifting. Is it shifting left? Can't remember. We basically reduced our error surface area because the compiler did more checks for us. And as we know, compile time errors are much better to deal with than runtime errors. But yeah, the top one is all about programming speed, the program running speed. There are very few instances where you actually would prefer the program to take the brunt of the loading as opposed to the compiler. It's like nearly always better. Before constant expression, they used to have these, I wonder if I can find it for you, Metaprogramming factorial C++, because constant expression was a C++ 11 feature. And before that, they actually used to have the ability to do this stuff. except they do it all wacky like with templates. It was really interesting. I'll just show you this randomly. It's totally unrelated, but a bunch of you are probably interested. Is like what you would do is you would go and create a templated type, a templated class in this case called factorial. And what it would do is it would have a value inside of it, and its value would be enumerated to like n, the non-type value, the non-type parameter, n times factorial of n minus 1. And if you think about how template instantiation works during compiler time, what happens is you say to the compiler, hey, I need a factorial of 4. So what it does is it goes, oh, they need a factorial of 4. Let's go quickly. We'll make a struct. We'll replace n with 4. We'll replace n with 4, so it's n's 3. And then they go, oh my god, we need a factorial of 3. So then they go, oh, well, we better make a factorial of 3. Okay. And then we need a factorial of 2. You know, and it basically does this. Essentially, right? Goes down and down and down till you get to factorial 1, where it says we need a factorial 0, but then you've hard coded in using explicit specialization what a factorial of 0 even is, essentially. And now what you've ended up doing is your compiled program essentially ends up looking something like this, where at runtime now all it has to do is quickly like punch those values together. Actually, it should do it at compile time because it can pull that together. Let's see if we can actually run that code real quick. Again, you don't need to know this. This is just me kind of showing you that like this has been a topic on people's minds for a long time, even before C++11 when constant expression was written. And this is kind of where you get into that topic called metaprogramming. Yeah, so you can see in this case that it would manage to reduce it down to that, which is very interesting as a topic. But again, it's very verbose. You can see kind of why that's not a lasting aspect. So Suluk says maybe a triangle number function will be better since repeated sums will reach the bounds much more slowly. Yeah, exactly. So what we're talking about there is that I was trying to write this function that would like take forever to compile. But what I was doing is not probably a very good one. You would probably need something that like, I don't know. I don't want to waste too much time on it, but you'd basically say, yeah, return n plus factorial n plus 1 or something. I don't know. Would that even make sense? Sure, maybe. I don't even know. I'm just kind of, I probably should leave this one alone now. All pass through this function will call its... Oh, yeah, of course. Silly me. Yeah, still pretty quick. It's really interesting. I'd never thought about that. Basically, integer factorization of a very large prime number. Yeah. I think I'll leave it there. But I mean, I like that we've kind of demonstrated that. I mean, what's cool about this is that it kind of shows you that you know oh wait, sorry, this wasn't constant expression either. Ooh. Silly. Right now, yeah, okay. Oh, max, there you go. Maximum depth of 512 calls anyway, you know? So you're not even going to run into a problem. I mean, that's recursive naturally. You don't have to use recursion for constant expression, as far as I understand. I'm sure there's non-recursive examples out there. And there's probably some examples out there of code that runs really slow. But what I like about what we've kind of shown here is that there's very little penalty. You know, like we've nearly tried to write code that the compiler just will be like, oh my god, that's so complicated to handle. But it's like, you know, if the program can run it in a reasonable amount of time, the compiler can then probably calculate it in a reasonable amount of time as well, which is interesting. The last thing that we kind of have to go through as part of these slides, variadic templates. This is definitely where, I mean, it's kind of the last slide of content in the course, if you think about it, which is pretty exciting. Variadic templates, I always describe it to people as it's like the printf thing. How, when you do a printf, you can take in like some unbounded number of arguments, because when we write C-like programs, we're kind of taught you have a function called blah, and it's going to have one parameter to, maybe it has 3 in a default, but if you want it to have 5 or potentially 5, you have to go and write 5 parameters there. If you want it to have potentially 10, you have to write 10 parameters there. But variadic templates are a really cool way to use our templates in C++, using a little bit of extra syntax that, again, is not really that critical in the course, but is useful to know. It looks a lot like a JavaScript spread operator, but essentially what it allows you to do is to say, I want to create a templated function called print, where it's going to take in a type A, and then it's going to take in a remaining list of types called B. This syntax is super boutique, and it's really, I think it's hard to reason with because it doesn't look like anything else you really deal with in C++. But this is us writing a recursive templated variadic function where we say, okay, I've got type A, and then I've got all the other types, which I'm going to call B, and then what I'd like to do is call print, and print expects a single type, takes in a const.l value reference, and it says, yep, I'll call that for type head. And then what happens is it calls tail with all the remaining types. Now, this can be really confusing. So what I like to do to make this a little less confusing is actually kind of show you how the compiler will think through stuff. So let's imagine for a second that we call this one here, keep it simple. I call that. Okay, what happens is I've called print with type A of 1. It is similar to Python, definitely. Type A of 1, and then type B is the collection of a float and a string literal, which is a const char star. So what happens is that function here, when it tries to instantiate a version of it, it does print where A is int, and then it gets B with all the rest, and then it simply calls print on A and then print on all the remainder. But print on A will naturally then come to this function here, and it will instantiate that and say, yep, type here, T here was an int, and it'll call that. And then print B, well, it needs to instantiate itself too, but it's still of the variadic template. So then down here, you end up getting this one where it says, okay, well, in this case, A is float, B, should call it float, head, const char star tail, does that. And then it says, yep, now we're going to print head and we're going to print tail. Print head in this case. In fact, I think tail would just be like that. Yeah, and then print head and print tail, well, it's just going to go and get that base print function there and do it for float and do it for const char star. Because it's a template, I think it would do some reference collapsing, I'm sure, with that one. Not sure. It's interesting. I guess so. I actually don't know what would happen there. What does it say on our slides? Char star const reference. Yeah, okay. We would just get a char star const reference. That kind of makes a lot of sense if you think about it. Because even though it's underlying type as a char star, I guess C++ makes it a little easier to deal with. Yeah, that's variadic templates. So the point of showing you variadic templates is to show you that, there are people out there who will be writing this code. Imagine scenarios, say like, I don't know how the Python args and kwargs, quargs and stuff is implemented, but if you did have to write something that could take in an unbounded set of parameters, then you would be able to use templates. You would be able to use your knowledge on binding to think about how different types, reference collapses they're passed in. I mean, there was this question earlier from Sulux who said, not going to lie, I'd appreciate somewhere where all this compilery stuff could be taught, if not for interest's sake, if only to make some of the more obscure text in the reference more understandable. Yeah, so I mean, there is a course in CSE called Compilers and Programming Languages. I studied that as a student years ago. I would recommend people study that. Again, I think Jingling designs exceptionally good assessments, and I loved that course. I wouldn't say they go super deep on stuff, particularly with compilers. That one's probably more like a programming languages. Makes you think about programming languages and you write a compiler. But I like it too. It makes you really think about how programming actually works. So I definitely think it's super interesting. And I know there's some things that we could probably go into more detail with. And then for background, it was a lot of like the rewriting of a lot of the course happened with actual C++ developers who were like, I've never seen this actually come up or anyone actually sit down talking about reference collapsing in any detail, like basically maybe once in 3 years. So we were like, well, it's probably getting a little bit too academic at this point. So that's kind of the background of that. Isn't Jingling also the one that designs especially hard exams? Well, they did for me, but that was 10 years ago. So it's hard to tell. Also, exams are probably different now. It's not based on C++. I think it's... I don't know. Go look up the course. Again, I did it in like 2016, I think. So it's probably changed since then. I'm just going back through some of the other questions. So before we kind of wrap up and just go to assignment 3 stuff, I will come back to this. Let me do a follow-up when it comes to the double brackets. I just missed it in prep and I noticed it when I was talking about it. There is a detail there, but I want to again get my answer straight for you. It's very obscure kind of thing though. I mean, I don't think anything will be obvious unless I get lucky. Sorry, looks like one sec. Looks like the webcam randomly needed to disconnect and reconnect. Let me try it out. Yeah, it's not happy. Oh, one sec. There we go. Webcam. Oh, it's very warm. Okay. Yeah, sorry. So bind 1, bind 2. Oh, we didn't really compile that code, did we? Let's try and compile this code really quick. I'll just go steal this one here. Cool, bind 1. Bring up the terminal, make bind 1. What do we got? Yeah, the ampersand's in the wrong spot. We know that. Declaration of reference variable y requires an initializer. Oh yeah, it's a reference, sure. So it needs to be like x or something. Unused. Yeah. Void x. I know. Yeah, let me just dig into that. It was some really obscure thing that was written into slides many years ago, so I'm not 100% sure on that off the top of my head. But yeah, let me loop back to you on that one. I think that was it actually. Yep. Okay. Well, yeah, I think let me look at what questions we didn't answer. Maybe it was way up the top. I'll get back to like anything unrelated to this lecture. I'll get to after. Oh, you asked what does near the end of the lifetime mean? That's what I mean. There's a very detailed definition. You can kind of look that up. X values, PR values. I don't have a strict definition for you on that one. Like, we don't ever expect you or go into any detail with X values or PR values in the course. It's mostly just to kind of throw at you and be like, you will discover if you spend time looking through the C++ literature that things aren't just as simple as L values and R values. And even then, some people argue L values and R values is getting a little bit deep into things too. Oh yeah, I think this is the one I missed. Why did the last slide of decltype say will not work? Good question. Sure. So this was probably a slight detail that I glossed over. Basically, where is it? Here. Basically, this is one of the few times, as far as I know, that you actually need the new function syntax. And again, I can't tell you that I've spent extensive amount of time trying this out myself, but it is what I'm educated on, at least, is that if you come in here and you just write decltype begin, that will not work, because as the compiler parses through this stuff, it doesn't yet know what begin is. However, when you do this, the compiler now knows what begin is because it's actually processed the parameters. I wouldn't put $1 million behind that, but I'm pretty certain that's what's going on. It's a really obscure thing. Yeah, it is referring to the previous slide. It's not very well written there. I'll acknowledge that. It's basically saying like, hey, what's the return type of this function? We know it should be declaration dereference begin. However, that won't work as begin is not declared yet. So we have to use the new function syntax so that begin is declared at the end. To reference it at the end because the type is known here. Whereas the other way around, the type is not yet known at this point. The compiler would be like, I don't know what the name beg is. So that won't compile using the old function syntax. Yes, but what I'd preface with this is because these slides are getting into like really obscure territory, this would be something that I tried once like 7 years ago, and I haven't spent a lot of time like messing around with these particular examples again because it's quite academic. So I'm pretty certain, but it's hard with new versions of things because, you know, maybe they've patched it or something like that. So again, take it as probably certain, but, you know, for every 100 things I say that are probably certain, a few will be out of date. Cool. Sounds good. It's always a bit of an awkward one, this lecture, and we keep cutting it down. So I do apologize that it might not feel as punchy as some interesting lectures with smart pointers or templates or polymorphism, but these are the oddball topics that are really obscure and are always kind of on the edge of whether we think they're critical to the course or not. So yeah, I just appreciate you spending the time to sit through them. Thank you.